So we've learned about the geometric series and telescoping series, and then in this section we saw the harmonic series. But the harmonic series is actually a special case of this series, which is called the P series. P stands for power. Just say no. Power series. And the harmonic is actually a special case of this, and I'll show you that in a second. So recall from section 8.9, there was a typo there. It said 8.8, but it means 8.9, that we already learned this about this improper integral. If a is greater than 0, right, a being the bottom part of your integral, then the improper integral from a to infinity of 1 over x to the p, x to that power, dx converges if p is greater than 1 and diverges if p is less than or equal to 1. So we already learned that in section 8.9. And so now because of the integral test, that means that the series that I would build from that function, right? So here's the function. So that creates this sequence and therefore makes this series. So the power series that is built from that power sequence that is built from that power function right there will converge if p is greater than 1 and diverge if p is less than or equal to 1. Now you'll notice that or equal to. See that right there? The or equal to? That means that if p equals 1, that's the harmonic series. All right, my highlighting didn't work very well there, but it's an or equal to bar. And the or equal to part would be 1 over k period, right? So 1 over k. And that diverges, right? That's the harmonic series. So the harmonic series is actually a special case, and it's the borderline between convergent and divergent. Everything greater than 1 converges, everything less than 1 diverges, and everything equal to 1, which is the harmonic series, diverges. All right, so now we're going to use what we know to answer whether the following series diverge or converge. And there's a little bit of a trick in here. All right, so this one, let's start here. Now we learn back in pre-algebra, a long time ago, that negative powers mean you have to turn it into a fraction. So you make it go from 2 to infinity, and it becomes 1 over k to the 0.6. Okay, well that fits my power series. My p-value is right there. P is 0.6. 0.6, last time I looked, is less than 1, right? Therefore, this is a divergent p-series. P-series, we don't actually know what the values are, unlike geometric. Geometric series, we know the values. But a p-series, we won't know the value, but we do know whether it converges or diverges very quickly because they just follow these particular methods because of the integral test. So p-series you like to see a lot of because p-series are very simple. Less than or equal to 1 diverges, greater than 1 converges. The equal to 1 part is actually the harmonic series. All right, now I lied to you a little bit because I say in the instructions, oh, these are p-series, but that's not true. This one's not a p-series. This is a little review question because this is from k equals 1 to infinity. 6 to the negative k would be 1 over 6 to the k. That's a geometric series, right? So this is geometric. And it converges. Let me just remind you about geometric series. It converges because the ratio r is 1/6, and 1/6 is between -1 and 1. So this is a convergent geometric series. It's a lie. I said it was a p-series in the instructions, but I lied. Just a little review. A is 1. Your r is 1/6. And I keep saying that. It converges because your ratio is 1/6, which is between -1 and 1. Now, if you're thinking, oh, right, we had that formula, and I know that it's a over 1 minus r, not so much, because it has to start at 0. And if you look at this problem, it doesn't start at 0. It starts at 1. Now, if you did want to find the value, I can tell you that, just as a quick review, if I have this series from 0 to infinity of 1/6 to the k. That would be a over 1 minus r. So that would be 1 over 1 minus 1/6, which I did it in decimals, 6/5. So that would be 6/5. And then to find the value of what I was given, which starts at 1, I would subtract away the 0th term. So I subtract away what happens when I put in 0. So when I go from k equals 0 to 0, that's a 0, of 1/6 to the k, that would be 1/6 to the 0, which is 1. So this particular series, just as a little review, from 1 to infinity of 1/6 to the k would be 6/5, take away 1, which would be 1/5. It didn't ask for that, but just as a little reminder and review of that from geometric. Geometric, of course, is rare because we actually get to know the specific value, which we don't really generally get to know. For example, in this p-series, we don't know what this p-series diverges. Well, we do know this is infinity, so it diverges. But this one, this is going to converge, but we're not going to know what it converges to. I put these two side by side because students often get the two of them confused. This is a geometric series. It's a ratio raised to a power. This one starts at 5, goes to infinity, and it's 1 over k to the 6th, right? So this one has the k in the fraction and then raised to that power, and this one has the k as the power. So this is geometric, and this is a power series, okay? So just to help you not confuse the two. So 1 over k to the 6th. Now you'll notice your power right there. That power on letter A was 0.6, so that was divergent. But on letter C, 6. So your power is 6, which is greater than 1. Therefore, this is a convergent p-series. And we don't know what it converges to, but we know that it would converge. Basically, the only ones we do that we know what they make are geometric series and telescoping series. All right, so let's determine whether the following series converge or diverge. And you're thinking, oh, well, they don't have anything to do with what we're doing. Oh, contraire, they really do, because this is a power series, right? This is a convergent power series because you can see, right, your power is 7, which is greater than 1. Therefore, this is a convergent p-series. Done with that. Okay, now letter B might not seem to be related, but it is if we rewrite it. So we would rewrite it from 1 to infinity, 1 over n to the half, right? Because a half power is a square root. Okay, well then my p is a half. 1/2 is less than or equal to 1, therefore this is a divergent p-series. And just to give you an extra one, just so I've had students ask me about this, so let me throw in a letter C right here. If I had from, I don't care, n equals 3 to infinity, 1 over n to the negative 7, right? So very similar to this one. Just going to kind of add this part in. That would be the same thing as the n equals 3 to infinity of n to the 7th. Now let's think about that for a second. You're taking a number to the 7th power and you're adding them up. Well, it's divergent. Of course it is, right? It's very much divergent. But you can see it right here. Your n, not your n, your p, your power is negative 7. Negative 7 is less than or equal to 1. Therefore, this is a divergent p-series. Now, by logic, it just makes sense, right? You're adding up something to the 7th power infinitely many times, so no duh, it's divergent. But it's something positive, to the 7th power, which we are. And so this is always positive, 3 to infinity. So the n part is always positive. So you're taking something positive to the 7th power and adding them up, and just keep going. Well, of course that's infinity. infinity rather quickly, as a matter of fact. So it's a divergent P series. But you can see it that it still holds. It doesn't say anything in here about negative or positive. It just says less than 1, right? Therefore, less or equal to 1, excuse me. So therefore, this is still divergent.